and we move on to fishing for p-values. This figure shows the number of worldwide non-commercial space launches in red, plotted alongside the number of sociology doctorates awarded in the US in black. Space launches belong to the left axis and the PhDs belong to the right. The correlation coefficient is 0.79. The sources are the Federal Aviation Administration and the National Science Foundation in the US. And presenting the data like this suggests that we think there is a causal relationship between these two variables, right? Like we did with SIDS and prone sleeping. Perhaps one causes the other, or maybe they have a common cause. The truth is, of course, that the creator of the figure, Tyler Vigen, has just been looking for correlations between all sorts of variables across all sorts of datasets. His website is full of these graphs, and some of the correlations are astonishing. For example, there is a 99.8% correlation between US spending on science, space, and technology and suicides by hanging, strangulation, and suffocation. Now, Vigen is obviously not trying to claim that the US should cut down on their spending on technology, but rather the site illustrates how it's possible to present data in a way that suggests a causal relationship between variables that have nothing to do with each other. This is classic p phishing or p hacking. In register epidemiology, it's often very easy to go fishing for results because we have so many variables. For example, if we want to know if pregnancy-related maternal illness affects long-term social outcomes in the children of the sick mothers, there is a number of illnesses such as gestational diabetes, hypertension, inflammations, and so on, and a number of outcomes such as employment status, education level, income, marital status, and so on. If we have 10 potential illnesses and 10 potential outcomes, we are almost bound to find something if we just look at all 100 combinations. And in addition, we may include any number of adjustment variables in our analysis. Sex, socio-economic background, birth weight, immigrant status, and so on. And we may define the outcomes in different ways. Education level could be university versus not university. It could be years of education after primary school, and so on. In principle, there are hundreds or thousands of p-values available to us in this situation. It could be tempting to just focus on, for example, inflammation versus years of education adjusted for sex, because that yielded the lowest p-value. But unless we are clear about how the process that led us to choose this analysis or this focus, we are guilty of p-phishing, especially if the results change substantially when we adjust for socioeconomic status or something else. However, if our research question the whole time was about inflammation and education, and we did not conduct all the other analysis, it's okay. Considering the graph, if somebody without looking at the data had made a model that predicted a correlation between non-commercial space launches and sociology doctorates awarded, this figure would be strong evidence in favor of that model if they had specified the model beforehand. And this was the case with prone sleeping and SIDS, right? This website provides a wonderful tool to illustrate the principle of p-phishing. They call it p-hacking. It's not epidemiological data, as we will get back to very soon, but the concepts are all the same. Now, in the US, they have two major political parties. Uh, the Republicans and the Democrats. Uh, we are now social scientists, and we want to know if the US economy is affected by whether Republicans or Democrats have the power. Now, this is real data going back to 1948. Of course, we want the p-value right there on the right to be less than 0.05. So let's start out by seeing if the gross domestic product, or GDP, gets bigger with Democratic presidents. So Democrat president. Unfortunately, it doesn't. P is equal to 0.8, way up here, which will never get us published. Now, there are 50 states in the US, and each state has a governor who is kind of like a president, but only for one state. So they sign off on legislation, they can pardon prisoners, and so on. So we're thinking that, hey, of course, it's not only the president who is important. We should include all the governors as well. This is brilliant. So let's do that. Now, P is less than 0.1. So now all we have to do is to write the paper, right? It even turned out the way us socialist Nordic people secretly hoped, that more Democrats gives a better economy, just like we already knew in our hearts. There are another group of elected officials in the US. Congress consists of the Senate and the House of Representatives. The Senate has 2 senators from each of the 50 states, whereas the House has more representatives from states with more people. This is similar to the parliament in other countries. So what effect does Congress have on stock prices? So we have the senators, the representatives, and the stock prices. Now, a p-value of 0.58 indicating no effect whatsoever. But what if we include employment as well? So we make a variable that is that consists of stock prices and employment rates. Okay, now we're getting somewhere. P is 0.06, very close to the 0.05 threshold, right? So we need to do something else. Perhaps it's wise to exclude recessions like the one in 2008, right? When the economy just goes down generally. So this is especially with stock prices and employment, right? The recessions have to affect these 2 variables. Ah, yes, P is now 0.02. But in the favor of Republicans. So that's not what we wanted. That Democrats have a negative effect on the economy. Now, obviously, we won't include this in the final paper. It goes against what we already know, right? That the Democrats are the best. So it must be a fluke, right? After all, Trump is a Republican. Now, what if we try inflation instead? No, P is less than 0.01, and the economy is worse when Democrats control Congress. Apparently, we need to change things up a bit. So let's go back to gross domestic product. There we are, just what we wanted. P is again less than 0.01, and Democrats have positive effect on the economy when they are in Congress. So the more Democrats, the better is the economy. So we now have our paper entitled GDP in the US increases when the Democrats are in power. Or you could write about how Republicans are good for employment and inflation. Okay, so finally, we'll talk a little bit about how to present and interpret multiple estimates. This is important in register epidemiology because we often have so many variables to choose among in our analysis. We may have several exposures or several outcomes or both. For example, we may study the effects of being born prematurely on health, education, work, and so on. This would be one exposure and several outcomes. We could study survival for different cancers, and that means several exposures, so the cancer types, but only one outcome, survival, right? Studying comorbidities for people admitted to intensive care units may be a little bit of both. So why were they admitted? How long did they stay? What treatment did they receive? That would be the exposures or the different health consequences are the outcomes. At a 5% significance level, we expect one false positive if we conduct 20 tests where the null hypothesis is true. And now this means that P will be less than 0.05, or the 95% confidence intervals will not contain 1 or 0, depending on what kind of test you're conducting. This is not a course in basic statistics, so I will assume that you know most of that stuff already. So how many false positives do we expect if we present 10 estimates? So that corresponds to testing 10 hypotheses. And let's assume that all the null hypotheses are true. The answer is about 1/2. So in other words, if we investigate the effect of being born prematurely on 10 different outcomes, and P is less than 0.05 for one of them, the evidence in favor of that association is not as strong as it would have been if we had only conducted one test. So we expect the lowest among 10 p-values to be quite low, even if there is no effect. We also expect the highest among 10 p-values to be quite high, but that's not as important. So in other words, the more estimates with p-values or confidence intervals we present in our tables, the more likely it is that the most significant is a false positive. So what do we do? And I'll pause for 5 seconds here and you can shout your suggestion at the screen again. So did I hear Bonferroni correction? That's 10 points to you. Now this is a good rule of thumb to use when discussing your findings. If you conduct 10 tests and P is greater than 0.005 in all the tests, you should be more careful about your conclusions than if, for example, p is less than 0.001, and maybe p is less than 0.001 in a lot of the tests. Now note that this only applies to the findings you intend to discuss, so your study variables. If you present confidence intervals for adjustment variables, they don't count, so to speak. So for example, consider the risk of long-term unemployment for adults who had cancer in their childhood. You may adjust for sex, socioeconomic background, and so on, but as long as you focus on the main relationship, which was childhood cancer, that's your study variable, and unemployment, that's your outcome. You can treat this as just one test. However, if you say something like, childhood cancer did not affect long-term unemployment, but this other adjustment variable, socioeconomic status or something, and then go on to discuss this variable, then you have to account for multiple testing, right? So then you have to say, well, if sex had a low p-value, we would have discussed sex. So that's basically a study variable too. So then all your adjustment variables become study variables. And this is a very easy sort of trap to fall into. You have your main hypothesis, and for some reason, maybe you're just wrong. Maybe you didn't have the power that you thought you would have. In registry research, that's very often not the case. But you don't get the answer that you thought you'd get. And you're thinking, okay, we won't be able to publish this in a good journal. And then you start discussing something else, something that was originally just supposed to be a detail, but you get this p-value 0.02. And then half your paper is about that thing instead of the main thing that you originally intended to investigate. Okay, that's all I had for these lectures. If you have questions, I suggest Googling them. Okay, thank you.